Hi there, this is the second of two videos for the two lectures that I'm missing. This one we're going to start talking about small signals. We're not going to do the math of the equations, we'll do that in class. What we're going to talk about is just the definition of small signals, and that should help make the model that we use. In other words, when we're using a resistor in a schematic, we use a model for a resistor, and that's V equals IR or whatever. We're going to start talking a little bit about the model that we use for a small signal, and that will become clear what I mean by that when we get there. Okay, so this is, we won't quite get to the common emitter analysis, but we'll go through the real small signal definition. Again, just a reminder, we're using transistors as voltage input devices, not current input devices. Of course, MOSFETs are always voltage input devices, but BJTs can be considered input or voltage input devices, but let's use voltage input devices for everything. Okay, and this is used later, but why not remind you now? When you look at the VCE or VDS versus IC or IDS curve, you have two distinct regions. You have the active region, we have the linear region. The linear region behaves a lot like a resistor. So if you need a resistor, you can put a device in deep linear region, and that works as a resistor. Okay, and then over here in the active region, that acts like a current source. In other words, when you change the voltage across the transistor, the current doesn't change much, and that's what a current source does. Okay, small signal definition. Okay, we talked a little bit about small signal definition. First definition we saw was small signal is a change in something over the change in something else, and gain is a famous example of that. You see, if I change the input this much, how much does the output change? Okay. And the units, it all depends on whether the output is current or voltage and the input is current or voltage. So if it's a voltage output, voltage input, then the V's cancel out and you're unitless. If you have voltage out, current in, now you've got resistance. Current in, voltage out, now you've got transconductance, or you've got conductance. Okay. This is a transfer curve. You have input on the x-axis and output on the y-axis. That's a transfer curve. It sees how the output changes when the input changes. And right here you can see a section of this graph that's pretty linear. That was the second definition of, the second piece of the definition of small signal that we talked about. What you have to have is when you change the input, the output has to change linearly. So that's a legal small signal region. This still has some gain here, but since there's this curve in the graph right here, that we can't use that in our hand calculations, our hand small signal calculations. Okay, so there's the amplification region, and inside that, generally, when there's some curves, those have to be removed, and linear part, that's your legal small signal region. Okay, so the final piece of the small signal definition comes from the superposition theorem. Won't go into the superposition theorem here. Hopefully if you wondered why we simulated and tried to prove the superposition theorem, that was to remind you what the superposition theorem was, so we wouldn't have to talk about it in class. And you go back and review. So the superposition theorem says you zero all but one source, figure out the currents and voltages at the nodes and through the branches, and then you zero out all but another source, you do the same thing, and then superposition says that, oh, if everything was linear, then you can just add those currents, voltages, and you get what the actual full circuit with both sources in, you get the voltages and currents. Okay, where does that come into play? This is a random circuit here. You won't see anything like this in this class, especially since there's an inductor in there. Inductors, again, for high frequencies. We won't see it in this class. But capacitors, here's an AC coupling cap, here's a bypass cap, here's another AC coupling cap. So everything in the kitchen sink thrown into the circuit as an example. Okay, when you look at this circuit and say, so here's just a bit on notation. This is a small v right here. In general, for when if you have an uppercase V right here, it means this is a DC source. This right here, it's a lowercase, but generally lowercase to me means just the moving part of the signal and not the DC part of the signal. For a combination of DC and AC, you have a combination, let's say a large V and a small s or something like that. So this notation isn't exactly what I like, but what this symbol means right here is, yes, you have the biasing circuitry plus the small signal on there. I guess this could be just the small signal here, so you have the biasing here. So yeah, so we've got a moving signal here, but let's say we zero this out. That means all the rest of the sources, VDD, ground, or minus VSS, those are DC sources. So the only moving signal here is this one right here. If we zero this out, call this 0. Say, oh, there's no signal on top of the biasing, we're not injecting a signal. If we say this is 0, then there's no other moving signal in the circuit, and we can take this, we can look at the components, how they behave under DC. And under DC, a capacitor is an open circuit. So this becomes an open circuit. Okay, this becomes an open circuit, so that disappears. This becomes an open circuit. Inductors become shorts, and that's what you see right here. You see the inductors become a short right here, turns into a wire. This is an open circuit, so it disappears, and the output, it's an open circuit, so that disappears, plus this is disconnected. And that's the DC equivalent. That's what's left over. And if you were finding large signal, and in other words, the biasing voltages, that's the model that you would use. That's the circuit that you would use. Okay. For small signal, we turn this on such that it's a high enough frequency to make the capacitors shorts and make the inductors open circuits. So again, when we're doing the AC equivalent or the small signal version of the circuit, put this frequency high enough such that all the capacitors become open short circuits, and the inductor becomes an open circuit. If you look at that now, the inductor becomes an open circuit, so this disappears. So this path to VDD disappears. This becomes a short, so C3 becomes a short. You have a short to the resistor. Now this one shorts, which means this is connected to ground, which essentially makes this RS disappear. This capacitor becomes short, so this whole thing, this becomes a wire. And here is your AC equivalent. Okay. Notice maybe a couple things here, that this minus VSS. This minus VSS has become a ground. This is from the book, and if you're looking at the AC equivalent, it depends how you define AC equivalent, but what you'll see is, let me go back a step. Now that you have the AC equivalent plus the DC equivalent, if you just happen to be working in a range where you can consider everything linear, remember back, if you're working in this region right here, the input, the change in input versus the change in output, that's pretty much a constant in this region. If you're working in a region that's linear like this, you can use superposition and say, well, the behavior of this entire circuit right here is going to be a superposition of this circuit and this circuit. Okay, that's the big secret to take from this. Okay, so if you find the DC equivalent, figure out how it behaves. Find AC equivalent, figure out how it behaves. Then you can sum what you found to find the behavior of this whole big circuit here, if you are in a linear region on your transfer graph, on your transfer curve. Okay, so that's the missing piece of small signal analysis, is that what you're going to actually be doing is you're going to be analyzing the AC part of the circuit. This is large signal. Yes, you absolutely need it when you're building your circuit to figure out the currents and voltages. But when you're doing small signal analysis, maybe I should add that word on there. When you're doing small signal analysis, in other words, paper calculations, what you're going to be doing is looking at this version of the circuit. Okay, just this moving, just what happens when you move things. Okay, so now back to this voltage right here. So since you're in a linear region and you can use superposition, remember superposition says you zero all sources except for one. This version right here, we're looking at this moving signal right here. So all other sources get zeroed. All other sources get zeroed. Over here, this is large signal. You could, since we're saying we're operating in a linear region, that's weird to say because this says the input isn't moving. But yeah, so, oh goodness, now I've got, let's see, how can I fudge this? Now this is for DC biasing, you need to have these actual voltages in your circuit to figure out your VGS or your VBE and your currents and all that. Over here, when you do your small signal analysis, you have to take, you have to keep in mind that the secret to make why all of this analysis, the small signal analysis works, is because you're using superposition, which means only one source can be turned on, and this is your source. You only have one moving signal in your circuit, so you have to zero all the DC circuit, all the DC supplies right here. I would love to re-record that, but again, due to time. So yeah. Okay. Let's see. What's the next? It's for MOSFETs, but again, anything that you say for MOSFETs for is true for BJTs. If you replace this with a BJT, you'd have the same DC equivalent, except that would be a BJT. You'd have the same AC equivalent, except that would be a BJT. Okay. All right. Okay. And this, now we come back to part of the small signal definition we talked about in the last video, where if you take the curved parts into account, you get these higher order terms up here, but if you stay in a linear region, then you get to get rid of the squared, the cubed, all the way out to the Vn to the infinite term, and you end up with that, which is a line, and then the math becomes easy. So let's see, what do we have here? We have small signal is the change in something over the change in something else. It has to be in a linear region in the transfer function, okay, to get rid of the higher order terms. It is actually a piece of a superposition problem where you get rid of the DC part and you just take your single AC source. So all the circuits we'll look at will only have one moving source this quarter. So one moving source, I guess that's a lie. We'll see differential pairs later in the quarter, but we won't do small signal analysis on it. Okay, so we use superposition. Just take the AC equivalent of the circuit and do analysis on that, which means you get to zero all the DC sources. So superposition, linear region, difference over difference, and that's your true definition of small signal. Okay, we went through this. Okay. All right, so I think I'm actually gonna stop there on this video. Hope I didn't. Let's see. It's gonna self-deprecate again, but yeah. Stop there, and again, remember, linear region, change over change, and it's the AC part of the circuit that we do analysis on. And because we're in that linear region, we can take the AC part, calculate it separately, take the DC part, calculate it separately, and then if we need to, which we won't do, we can add those together using superposition to get how the complete circuit actually behaves.